evangelist in the DevNet team at Cisco, and I have the pleasure of being your host. And we have a great set of talks here focusing on when apps meet analytics. And I think you'll see we have an interesting set of talks that covers different areas of analytics. Of course, analytics can be applied in a lot of different areas. We have this one on neural networks. We have one on DevOps. We have one that talks about network data and when you apply analytics to that. And so I think you'll find this very interesting, both whether you're a developer that's looking to tap into this information that's available and do something with analytics with it, or even as an end user, changing our lives every day when people are applying what they can with data sets and analytics to solve problems like what you're seeing with Uber and Lyft and the way that new business models that they brought in. So, or even just using mapping software to figure out the best route to get for yourself, right, when you're driving. I think that's very simple examples, and we'll hear some better examples here. So with that, I won't take any more time. I'll turn it over to Chase Oakwine. Did I pronounce it right? All right. Perfect. Yeah, and you're with Keyhole Software?
Yes, sir.
Yeah, so he's going to talk with us a bit about neural networks, and we learned that we have a shared kind of fascination and appreciation with train travel. So I'm hoping you mix something into your talk about that. But
probably
with that,
won't, but
I won't eat up any more of your time.
All right, guys. Hey, I'm Chase. A couple things you probably noticed right off. One, I'm very tall. Two, I have an amazing belt buckle. Yes. So, a little bit about me. First and foremost, I am a servant. My goal in life is to help you be as successful as possible. You can reach out to me at any time via LinkedIn, via Twitter, etc., and I would love to help you in whatever it is that you're doing and make you better at it. I'm a Keyhole team member. I'm curious to a fault, and this is a big point. I love statistics, and that sounds like weird to say. I love statistics. If I were to go back in time to me at 18 years old, 19 years old, and say, hey, one day you're going to love statistics, I would look at myself and say, hey, where'd you get a time machine? And I'd be like, well, that's a good question. I don't know. So I have a big warning. This is important. We're going to talk about math, right? That's scary for folks sometimes, because I know a lot of us, we probably didn't come into this from a collegiate background, from an academic background. We got into the industry via whatever mechanism we did. Maybe don't have as strong math presence as some of our peers, right? But I believe in each and every one of you. I know that you can get this. Is there anyone here who can't add and subtract? Nope, everybody's good on that. Good deal. What about multiply and divide? We're good on that. He's a little fuzzy, but I think we're good. Awesome. You are all qualified mathematicians. You're all able to benefit from this course. The other thing I want to say is, I know I just said we're going to talk about math, and we're going to talk about neural networks. I've given this talk. Sometimes people go, hey, I didn't want to learn about math. I want to learn about neural networks. They are math. That's all they are. So I got a couple outcomes for you guys. One, I want to help you have a better understanding of some key areas around neural networks, what makes them powerful, why they exist. Two, I want to make you a champion at work. I want to make it so that you can feel confident going back into your workplace and saying, hey, I know enough now to be very dangerous. And this seems like something we should maybe look into, perhaps. And then three, I want to help you guys build the next big thing. There is a lot of potential in the industry for ways that we can leverage this, for ways that we can use this, for ways that we can be more powerful in what we do on a day-to-day basis in our businesses. And so I want to help you guys do that. So to start, I want to start with just a very brief demo. Normally this talk is 45 minutes, but I got 20. So we're going to cram as much as we can into it. I'm going to do a quick demo, 3 minutes. We're going to see how we can take images like this 5, this 0, this 4, and this 1, and some associative data that tells us that this is a 5, this is a 0, this is a 4, this is a 1. And we're going to take the pixels, these black and white values, we're going to convert them into numbers, we're going to crunch them through, and we're going to figure out what those, we're going to teach a machine to parse that. And so to do that, we're going to be using TensorFlow, and I'm not going to go deep into the details here. If you want to get with me later and you want to talk about the details, I will gladly show you in depth any of this stuff. But it goes like this. We have our inputs. We're going to take in 784 pixels. We have our weights, which we're going to talk about in a minute. We have some biases, which again we'll talk about in a minute, and then we have our predictions. This is what's going to be output. We want to output some predictions. TensorFlow has some nice sample data for us. It's going to make this easier. What we're going to do is we're going to find out how much error we have every time we do a run through to see how close to accurate are we. And then we're going to do this gradient descent optimization. Basically what this gradient descent optimization is going to do is say, hey, we have some error. We want less error. Make it less error, basically, in a nutshell. So from there, we're going to get some data. We're going to get some inputs, and we're going to get some known outputs. We know that this is what the output should be, right? And we're going to get a batch of 100, and we're going to test them. And so what we're going to do is we're going to feed that batch of inputs and the expected outputs, and we're going to get some predictions back, and we're going to say, hey, you're way off. Make it better. And we're going to keep doing that until it gets more accurate. That is basically, in a nutshell, how this works. So we're going to go ahead and start it off. Boop, boop. Make sound effects. I apologize. So this will take just a second for this to get up and running. Again, we're using the TensorFlow library. This example project is on the TensorFlow website, tensorflow.org. Waiting. This is exciting, I know. There we go, now it's starting to do stuff. All right, so what we see here, I'm going to go ahead and pause the execution. So this is the percentage of accuracy. This is how accurate are we getting. So we started off really not very accurate at all. We had like a 40% accuracy rate. And we start getting a little bit more accurate, a little bit more accurate, a little bit more accurate. We're already up into the 79% accuracy. And we're going to let this keep going. And this will keep going. And if I let it keep going, it'll get to about a 93 to 95% accuracy with this very basic setup. So, doesn't take a lot of code to get started. Again, all of that code is available on tensorflow.org, but let's talk about what it's actually doing, because that's the nuts and bolts of this. That's what we want to talk about. This is a neural network. We take in some inputs. We have some weights associated to those inputs, and then that gives us another set of inputs, which is this hidden layer. Then we have some weights associated with that. And then we have our outputted prediction. That is all a neural network is. That is all that it's doing. So let's first talk a little bit about what machine learning is. It's a branch of statistics, and basically it's just the ability to learn without being programmed. So to get a sense of that, we got to talk about statistics a little bit. What is statistics? Statistics is just the analysis of a large set of data. Now, what's interesting about that, statistics is relatively new. Statistics, as from a mathematical standpoint, is a fairly new form of statistics. I mean, it's a fairly new form of mathematics. And it came about from the study and collection of census data and tax data. So in Germany in the 1700s, they said, hey, we got all this data. We need to do something with it. We need to glean some insights. And so there was a book written called The Study of State, right? And it was how to be good at managing state entities, government entities, right? And that was where we got the origin of the word statistics. So just to put this into perspective, Euclidean geometry happened in 300 BC, very long time ago. Statistics didn't happen until the mid-1700s. We didn't get our first formalized books on what we consider statistics today around probability, averages, et cetera, until the early 1900s. So we're only about 120 years into statistics being a real thing. That's kind of powerful that we've done so much with it in so little time. Now, of course, as computer scientists, we know that we've just done a lot in general in that last 100 years, but to me, that's kind of amazing. So, why neural networks? What advantages do they give? Why would we use one? Well, most forms of machine learning use linear regression models in order to find out where we should be trying to solve for our problem space. But there are inherently some difficulties with this, and there are problem types that it just can't solve for. So with a traditional linear regression model, it looks like this. We've got some points of data. So let's say we've got some housing data. We've got square footage of home and price. So with a linear regression model, we can figure out this is the general slope of that data. So if we know the price, we can then extrapolate the square foot of home of what it should be and vice versa. But there's a lot of very simple scenarios where this just falls out of the window. So let's say we have these 4 pieces of data. True, false, 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 true, false, true, and true, false, right? If we look at OR, if we want to know OR, this is pretty easy to do from a linear regression model. We can just put the line right there. Boom. Everything that's on this side of the line, false. Everything that's on that side of the line, true. But what if we want to do an exclusive OR? What if we want to say it's only true if it's 0, 1, or 1, 0? Not 1, 1, that one's false. 0, 0, that's false. So this is what XOR looks like, right? So where do we put the line? Do we put the line here? Well, that's going to give us not correct answers. If we put the line here, still not correct, not correct, not correct. Because the correct answer is this. And you can't do that with a linear regression model. It's not possible to do that with a linear regression model. And so that's where the power of neural networks comes in, because it allows us to shape much more complex domain spaces. Now, this is a fairly simple domain space, but it gives you some insight into what is possible. Because imagine this, where instead of these 2 zones, you had 20 or 50 or 500, right? That's where the problem space gets more elaborate. That's where the power comes in, is the ability to make discrete choices within that problem space. So what are some of the uses for this? We heard in the last session here in the theater of a great use case using GPS data to help improve traffic fatalities and collisions. But we see a lot of it in image recognition, a lot of it around self-driving cars and automation, robotics, and my field of study and where I'm getting the most value out of it is around predictive analytics. Let's take some data about what's happened in the past, let's extrapolate that, and then get some value about what we want to do in the future, right? That's where I find the most value in it for me personally. Now, that said, it's entirely up to you and your problem space on what you want to do with it. There are a lot of problem spaces that it works out well for. So what are the parts of it? How do we assemble one? How do we put it together? So again, this is our basic network. We have some inputs. These are number values. We have weights. Think of these like percentages. So we're either going to make the input values bigger or smaller based off of those percentages. They can also be negative, so you can flip them around. That's going to give us a new set of values, and then we're going to do the same thing. That's going to give us a new set of values. So our inputs, again, just numerical data entered into the network. Hidden values are then calculated. The values of those hidden nodes and the weights, that's what the learning algorithm is doing. It's figuring out what these weights should be, right? You don't know what those weights are in advance. It figures that out for you. That's where the value of the learning program comes in. And then your output, generally it outputs a value between 0 and 1 that can loosely be interpreted as probability of whether I want to do this thing or not do this thing. Now, where most of us get confuzzled whenever we go out and try to find out information about this type of stuff is we see diagrams like this and immediately go, "Ugh!" Because this is scary unless you've been actively in academia and in mathematics. But this is really simple because it's just basic math. Everything that's going on here is just basic math. This is all that a neural network is doing at its core. And this is going to seem too simple for it to be true, but it is absolutely true. This is what's happening. This is basically what it's doing. 2 times 2 plus 2 times 3 equals 4 plus 6 equals 10. Right? We're going to take multiples of numbers. We're going to add them together. That's all it's doing. It's not any more complicated than that. There are some other elements to it, but at its core, that's really all a neural network is. So don't be scared of it, is what I'm getting at. So now, instead of just doing it with one set of numbers, we do it with large sets of numbers, graphs of numbers, and then it looks more like this, but it's still the same thing. It's still just this. This is all that's happening, right? To add on to that, then what we do in our hidden layers is add some nonlinearity to it. This allows us to make really discrete options and change the flow of the numbers and how the weights are derived and turn them into something meaningful. So again, all of that just translates into this. Now you'll hear the word deep networks a lot. What is a deep network? What does that mean? Well, all we're going to do in a deep network is add more of those hidden layers. So in between each layer, we're going to have new weights that's going to help us derive to an answer. Why this is powerful, this allows us to ask really complex questions. I don't recommend starting here. Start with something simple like this, but in very complex problem spaces, this allows us to ask really intricate questions. So I got a couple closing thoughts. So again, it's just basic math. Don't be afraid of it. Dig into it. Play around with it. Be wrong. Try again. There's a lot of stuff you can do. The thing that I'll encourage you, as you start learning, as you start going into these things, and as you start doing study in it, if you have a background in data analytics, don't treat it like traditional data analytics. You won't get as much value out of it. What I see a lot of people doing is trying to use this to go get KPIs. So basically, they'll take in some data and they'll ask the question, hey, I want to guess if this person makes $50,000 a year, because then I want to go see, because if they do, then I want to go market to them, right? That's the wrong question. The right question is, hey, I have some people, I want to make $2 million in additional profit next year. Who do I market to? Don't make those assumptions. Don't let your hubris make you think that you're going to create a better solution to who you should be marketing to if you only knew this, right? Leverage its power to then say, okay, this is who I want to market to, and in order for us to get to the margins and get to where we want to be, here's the data, here's how we get there, and let the machine figure out that for you. If you can change the way that you ask questions in that kind of a manner, it will powerfully change the types of questions you can ask inside of your organization, and it will powerfully add a lot of benefit to what you do on a daily basis. And that's not just in that one case with marketing, that's in any kind of use case. Think about actions that can take place rather than discrete values. Sure, you can get discrete values out of it, but ultimately that's not where the power is. The power is, what action should I take? What should I do? If you can ask those types of questions, you get a lot of value out of it. Again, I'm Chase. Please, if you see me around, I'm really approachable. I'd love to talk to you and ask as many questions as you want to, and I would love to help you. Thank you very, very much.
Okay, thanks, Chase. We do have time for a couple questions, if anyone has any at this time. Just raise your hand. I'll run over, give you the mic. Oh, yep. Great, thanks.
So just in that case, the number recognition problem that you just talked about, what were the inputs exactly? I was confused.
The inputs were the pixels. So there were 794 pixels inside that square. So we took the value of that pixel, 0 to 255.
Okay.
And we used that as the value, as the inputs. So each one of those
value
pixels,
being either black or white?
a range. So somewhere between 0 and 255.
Okay.
So there's 255 possible numbers
right.
that a pixel can represent. So whatever it was. So in some of those cases, on the edges of numbers, you actually have like closer to gray. So you may have like a 75 or a 125. So it's just whatever the pixel value is.
And so the output layer would be?
The output layer would be 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. So which number does it represent?
Okay.
So 794 pixels in, what number is it?
Okay.
Yeah.
So it's basically just classifying it into those 10 sets.
In that particular example,
By way
yes,
of that activation function.
Yep, yes, sir.
Okay.
Yep.
Great.
Question, thank you.
Any other questions?
So to get a little crazier, right?
Yeah, I love crazy.
I mean,
Good
so
at it.
what about a cat? What about, a
What
face
about a
of
cat?
I mean, so I'm getting an idea from image recognition that you see when you do, your CAPTCHA kind of things online.
Yep.
Like, what do you see? I'm just curious, how do you tell a computer about sort of the world? I mean, you can tell about discrete numbers, but
Yeah. So the way that it does that, and that gets into more complex types of neural networks. But generally, the way that we do that is, let's say we have a large picture. We break it into smaller pictures, and we scan across looking for a thing. And basically what we have is a lot of reference data that we initially say, this is what a cat looks like, right? Or whatever it is that we're training.
This block of sessions is over. And so next, Rob Schoening and Ashley Sun, they work at Lending Club, and they're DevOps space, and some of the goodness that comes out of doing that. And so they are co-presenters. They're going to have to share their 20 minutes. And I understand from Ashley that she has 10 years of karate and has earned a black belt. So I know I don't have to worry about Rob. He's going to play nice and share his mic time, or he'll be in a world of hurt. Oh, the clicker.
Here, you want to do it?
Okay, great.
Yeah, go ahead. Next slide. Hi, so we're from Lending Club. We're an online lending marketplace. We bring borrowers and lenders together, and borrowers get a better rate, and lenders get more money, better return, and we get a cut. So it feels good. And then today happens to be our 10-year anniversary, so it's kind of fitting here. So we're going to give 3 insights into the last 4 years of the evolution of DevOps at this company. I came on about the time that we had the first $1 billion of loans issued, and now I'm going to get in trouble with whatever I say, so I'll just say billions and billions. So we'll talk a little bit about what we learned over that time, and we're going to talk about how we use graphs to manage our infrastructure, and we'll have one demo.
All right, let's get started. So, number 1, who are we? To get this point across, I think a better question to ask would be, who are we not? We are not Netflix, and you guys probably aren't either. It's easy to look at companies like Netflix or Twitter or WhatsApp and try to emulate their success by mimicking their results. It's easy to read a blog post by Netflix on how we use Kafka with our Keystone pipeline to handle our data streams. And it's easy to say, wow, that's really cool. We should build that too. It's easy for this to happen too. But what's important to remember is that Netflix has Netflix problems. Twitter has Twitter problems. Lending Club has Lending Club problems. And if you implement a Netflix solution at your company, you may be solving a problem that you guys don't even have.
Yeah, I want to call attention to the top line there, which I think is relevant.
Yeah, so what's important is to figure out your company's problem and then to solve those problems. So you can't solve your company's problem if you don't know what the problem is. Similar to that, you can't automate all the things if you don't know what the things are. So looking at this slide, you probably recognize most, if not all of these tools. So how do we manage all of these technologies? We all face this problem of figuring out how do all these technologies work together? Do they integrate with one another? What if we want New Relic? Or what if New Relic doesn't play nice with F5? Does that mean we can't use F5? What if the integrations that we want don't exist? Are we going to make hundreds of REST calls to dozens of endpoints? No. So at Lending Club, we use graphs to handle all this information. And bear with me now, I'm going to go through a little bit of story time. But 3 years ago, we were dealing with very manual deployments. We were keeping track of our services on an Excel spreadsheet. And we realized we need greater visibility into our infrastructure. We need to answer questions like, is my app live? Are app revisions in sync across all of our environments? I mean, we couldn't even answer questions like, what the heck is out there? Like, what's deployed right now in production? So we created an internal application backed by a graph database to store all this information. And in the beginning, there was nothing in our graph database. But we sort of mimicked the life cycle of an app. And we thought, well, apps start in Confluence, so we'll integrate with Confluence. Developers and PMs create tickets and track stories through Jira, so we'll integrate with Jira. It'd be cool if our app can create tickets. Developers push to GitHub, we'll track commits, we'll track repos. We build and deploy with Jenkins. The artifacts get stored in Artifactory. We deploy to Amazon. That's a good one, right? We'll scan the Elastic load balancers, auto-scaling groups, EC2 instances. And since we have cloud in our app, we'll get our data center load balancer into our graph database. And if you combine load balancer information with our VMware server information, combine that with Jenkins, and you have fully automated deployments. From there, it'd probably be good to have monitoring in there. And so we just kept adding more and more to our graph. And I think you can see the growth of our graph model was, it happened very naturally and organically. So fast forward 3 years, we've grown from 5 microservices to over 400, and they all follow this pipeline, and it's a very smooth process, which is awesome. And so we went from having low service visibility to having a central graph model that we can query at any time, and that helps us make sense of our complex and interdependent infrastructure components. All right, so now that I have talked you all to tears, time for a demo. Talked about all this stuff, so now I'll show you some of the stuff.
So Ashley will be using Neo4j. That's the underlying graph database that we use. And what she's going to be showing here is she's going to live type the queries, and we're going to take real data. We've redacted a little bit of information.
Yeah. So this is my local Neo4j, but it is, again, from our prod database. I'm going to show you some of our AWS components. Right here, I've just typed in a super simple query just to show me our accounts. You'll see here there's 3 non-prod, prod infrastructure. And just to reduce some of the clutter, I'm going to limit the results to just come from our prod account. And so what I'm doing here is, this is a simple query again. It shows you everything that's in this prod account. You'll see in blue, this is the account. It's got some S3 buckets, it's got some SNS topics, and it's got 4 VPCs. So now digging into this one step deeper, let's say we want to see, well, what's in these VPCs? And you'll see now we get something a little more interesting. Hold on, let me zoom out. So in the blue, again, you'll see the account. You'll see the 4 VPCs in purple, and you'll see that each VPC has a whole lot of security groups and subnets. And not to belabor the point, but if we just go down one more level, that's when it kind of starts to get more interesting. If it will load. So now zooming out again, you'll see all of a sudden we've added EC2 instances, RDS instances, ELBs, auto-scaling groups, and the connections among them is pretty complex, right? Auto-scaling groups can contain instances. ELBs also contain instances. Auto-scaling groups are attached to ELBs, et cetera, et cetera. So yeah, this is just AWS, and there are more and more levels that we could go into, but I'm not going to go into all of those.
So what we have going on here is continuous scanning within our infrastructure. We go out and we talk to AWS. We talk to each one of the systems that Ashley mentioned, call their APIs, pull it in, dump it into Neo4j. So we have a database at any given time that's got 1 minute latency to get at this information. And it's very fast, and we can build all of our infrastructure on top of that.
Mm-hmm. So So next, that was the stuff. And the next is, well, how much does this stuff cost?
I'm glad you like that.
All right, so this query I have here, the EC2 instances that you saw just a minute ago, I'm querying for those, and there's a relationship from the EC2 instance to this label that we have called instance type, which just stores the type of the instance and the cost per hour. And this is displaying the monthly cost in descending order, grouped by account, region, and instance type. And it's a super simple query. We have reports generated off of this. And now let's say then that you're like, okay, this is cool. We see our AWS infrastructure components, but what about bubbling it up to our actual application? So we have a mapping for that too, where we can match our instances to our app definitions. Okay, and this, it's hard to type and write at the same time, so just 1 second. So what we do is we tag all of our EC2 instances with an application name, which includes our app definition, app ID. And so we'll match it by that, and we will return maybe the name of the app, the description, a service type, and we'll keep the rest the same. Hopefully this works. Okay, nothing. 1 second. Okay, so this is showing you the name of the app, right? And again, it's in descending order. How much is this app costing us per month? How many instances? What does it do? And then different service types, API, UI, et cetera, et cetera. And one last demo. What is this, right? I mean, how many times have you guys gotten this question from your boss or maybe your peers? What is this? What is this IP? So this one I'm going to copy and paste. But so here we have our app instance. This is a fake IP, obviously. And we're matching that to virtual server, pool, and virtual service, which are things that we're pulling from our load balancer. And then again, matching that to our app definition. And so we go from asking, what is this IP, to knowing exactly what it is. We have a host name. We have the app that's deployed on it, the revision, how traffic is flowing to this app, and lots of good stuff. And so we use queries like this for monitoring, alerting, our release and deployment automation, our cloud orchestration. It's all backed with by Neo4j queries. Okay. I'm going to hand it back to Rob. You can.
Okay, so to be successful with doing all this stuff, it takes coordination, right? And to get coordination, you need to get a lot of people to do what you want. And how to do that, what we've found, and again, just kind of key insight, is just to make it easy. Just as it was reasonably easy to get some information out about cost structures, that people will pay tens of thousands of dollars to do what she would put together there in just a few minutes. Make it easy and make it awesome. If it's easy, people will follow it. If it's awesome, people will follow it. That's all you really have to solve for. So make it so easy that people don't even think about doing anything else. Okay. Delivering 400 apps into production and without drama. I mean, I think you guys have all worked at places where pushing things into production is full of drama. We don't like drama. We like to be the Maytag repairman, sitting there waiting for nothing to happen. We want the money printing machines to be printing money, and we just sit there and make sure that nothing's really happening but making money. Okay, so in terms of the key insights, how to break that down, we'll break it down here in design, build, test, deploy, and run. Just some key ideas. For application design at scale, balance freedom and responsibility. And I heard earlier today somebody else gave a variation on this. which is to balance. To balance autonomy and constraints. So freedom and responsibility and autonomy and constraints. I think that's great. We've had fantastic luck with a unified pipeline. So build, deploy, test, run, unify that across the organization. Even if the technologies are different, unify that, get people to understand what it means to move applications through. Even if they look and act different, make them behave in a consistent way, and good things will happen. So if it's a Node app, if it's a Java app, if it's a Go app, make sure that it can be deployed, packaged, and monitored in a consistent way. Okay, this is a key one, operational metadata. It turns out that it's really important to deliver a quality product. In terms of deployment and being able to drive one car, you can drive one car, you can drive any car. Try to apply that to the way you run and deploy your apps, right? If you can deploy one app, you can deploy any app. So one of the greatest things that I see happening within our group, we can teach somebody how to deploy one app, and then they can deploy the other 399. They don't have to go to a wiki page. They don't have to go to a run book. They just know how to do it. Okay, and then at the run phase, transparency. And what Ashley was showing with Neo4j was one of the keys to that, is make all this data accessible, put it out in the open, and people will achieve success. So this is us. We do have some open source software out there that might be of some interest, and I think that's it. Mm-hmm. Do you have any questions?
Yep, we do have time for questions. We'll run the mic to you. Any questions?
Yep.
Ones I'm missing? I'm looking at the light. Okay, yep.
So in that Neo4j, when you zoomed out and you had all those relationship, lines, how did you build those relationships with all the probes and get them all tied together? Did you have a bunch of tags that were very specific to like a relationship type or something, or is that just native to Neo4j? Because I've never seen it.
So what we do is we're periodically scanning our in that example, right, AWS accounts, and we're making just REST calls to AWS, and AWS is returning information about auto-scaling groups or load balancers, and actually within that, it contains the information that you need to make that connection. For example, when you get information like describe auto-scaling group, it'll return information about what load balancer it's connected to. You use that, and you just create a relationship in Neo4j between those two nodes. And that just kind of builds up then the entire map of AWS or of our load balancer or of Cisco UCS, whatever you want.
Yeah, it is a Cisco conference. We do have UCS, so you can scan the UCS infrastructure, and it'll build up the data model. So we've taken the data model that's already there in the API, kind of inferred it, and then put something together. A lot of that is there in Mercator. There's some Docker support, some AWS support, UCS support. I forget what else we have in there. Very easy.
Okay, great. Any other questions? Still have time if you got another question. No? No questions? Okay.
Thank you.
Ashley, Rob, thank you
Thanks,
very much.
guys.
Okay. And, also due to programmatic interfaces, we can not only get access to that data, right? But then if you do glean something from it, how you can actually programmatically change it, right? Change something with your network, kind of create a closed loop system here that's acting autonomously, which I think is really neat. So, what do you need?
There's a problem, meaning how do you switch? Here we go. One second. Oops. Okay, here we go. Hi guys. So this is actually my first appearance at any Cisco event, and I'm very pleased to be here. This Sunday is my anniversary. My wife and I, we celebrate 11th anniversary. And she is like a huge part of what I do, right? So I'm a maker. And what I try to do is I come home after a long day of work, I take care of my kids, and then at night I sit and code. And the way I do that is by reading the docs, trying to understand how other people do things. So I'm copying a lot. But during the day, I work at Bank of New York Mellon, the biggest bank, biggest custodian bank in the entire world. And I thank them for their investment in innovation. The fact that I'm here is one of those things. And why I'm here to discuss how to collect data for, how to collect network data for this AI, for artificial intelligence. This is a very interesting topic because I don't know anything about AI, so anything that I say, check it in Wikipedia. But the basics of it is artificial intelligence is something about cognition. And cognition, there are a lot of functions in cognition, like thinking. And one of the hardest thing to do is to read between the lines. You know that sense that something is going to change, like you feel that, and this is why, because you inference, or you're making inferences over time, right, based on the facts that you know. And that's what we need to teach our systems to do. So what is enterprise networking? I'm coming from the enterprise networking space. I earned my CCIE. I've been managing networks for the past 20 years. I've been in technology for the past 20 years. I tried to get away from it, but it still sort of got stuck to me, and I'm back to it. So what is enterprise networking? It's like thousands of applications. It's not merely a portal where you support users and they hit one app. It's basically everything that works in the background, accounts payable, money transfers, SWIFT, whatever it might be, it's huge. There is a lot of storage, a lot of compute. Trying to move an organization, an enterprise, and I mean enterprise, where you have thousands of users, trying to move them all to the cloud is like a huge, huge mess. Try to raise, I challenge you, try to open your AWS account and try to build 150 nodes, compute nodes in AWS, you will fail. I guarantee that. So what's next for enterprise networking is big data integration. So we have a lot of, we work in silos in the network space, and we really want to keep our data close. So we have our SolarWinds, NetBrains, whatever, and we don't want to share. That's the kind of big concept. So what we need to do is we need to take that data and give it back to the enterprise so we can connect things around us. And at the same time, what we want to make other people do is do the same. So share that data in a graph model. So for example, the previous conversation was about graphs. So it's sort of, I'm continuing there. So what are the drivers for the next thing, for the big data integration? Because everyone wants automatic provisioning. They want to build everything instantaneously without problems. They want business-oriented management plane. So in Cisco, there is something called data plane, so those ASICs. There's a control plane, that's something that interacts with devices, and there's a management plane where there are smarts there. And Cisco takes that model to a point there where all of those planes, they sit inside the same router. And now we all go to a decentralized model where we have data plane devices, then we have controllers, and we have management plane. So in terms of Cisco, if you heard about Cisco Data Center and Network Management Suite, it's like both a controller and the management plane, and it pushes configuration up to devices. We want predictive fault indication and repair. So what happens is, let's say you have two links and you operate from a perspective that you have redundancy, but in fact, if you lose one link and you don't know about it, you're now in a state where you're in a soft fault state, meaning you failed, but you don't know about it, and it will bite you later when the second link fails. So graph databases, and artificial intelligence related to that help you understand whether you have a backup. Automatic optimization is basically, okay, I have endpoint A, endpoint B on the network, and I want instantaneously know what do I need to provision in terms of routing, security, quality of service, all the way through. How do you do that? So you take two endpoints and you figure out how can you physically go there, right? So layer 2 path. Then you go, do I have a layer 3 path? If I don't have, I build where possible. And all of that can be solved with graph databases. So what are the challenges? A lot of processes and no continuous integration. So people on the business side, they're not catching up to IT where we have continuous integration pipelines. You speak about Travis CI or Circle CI, they're like, oh, what's that? You have lack of automation and development skills, like we really need people, all right? So anytime you hear someone who wants to learn that, share as much knowledge as possible. So they will be inspired to do the same. Legacy infrastructure. It's very nice when you have AWS, but what if you have old legacy equipment that you bought from Cisco 10 years ago? And there's a lot of that. So if you bought a switch, it may not have an API, but what it has shell, all right? So, and in a lot of cases, you can't even get to it via SSH, you have to use Telnet. So how many people know about TL1? Anyone? So TL1 was a protocol to interact with optical devices that connect intercontinental optical links. So if you're in a big bank and you had that optical connection between, let's say, London and New York, that's what would you manage with, like TL1 was the thing. Now everything goes to APIs, but that's a slow migration. Now, lack of willingness and methods. So if I don't want to share, I will not share. And likely that other people would not be able to get data from me, so they have to have ways to figure out what I know, and that's called organizational knowledge. That's what people have. That's what provides job security. So that's a challenge, because some people don't want to share. So how do you overcome the challenges? So you use some kind of orchestration tool to collect the data. So data is power, and that's what provides you the basis of knowledge about what's going on the network. Then you take that data, you put that into a Git repository, you source control it, so you have a timestamp on everything, and that basically takes the image. Why do you need to do that? So later on, you can always come back to that raw data and redo whatever you're doing, like reanalyze that to apply AI in a different way. Maybe you later on will have better tools. RDF triples. So there was a question before about how do you actually create those connections between two nodes in, let's say, Node.js. So the way how you create connections is with resource RDF, and I will speak about that. How do you query that data? You use one way to do that. Neo4j doesn't have that, but I use personally Sparkle to do that, to retrieve that data. How do you provide people with access to data? So there is a thing called ontology. Ontology is a description of data that's machine readable, and it helps, like there's an enterprise ontology that basically each department creates their own ontologies, and they describe all those relationships and nodes in a graph database. All combined together, it allows someone to go into that ontology, it's a file, we'll see that, ontology, and basically understand, like, do they have the data that I need? So let's say if I go into ontology and I search for an IP address and I cannot find anything related to IP address, chances are there is no networking information in that ontology. Means the organization would unlikely be able to provide like statistics related to like metrics related to networking in their big data platform. Graph databases, as discussed, so Neo4j is just one. And you saw on the screen, I think the performance of it when you try to put a lot of nodes, let's say it cannot draw 60,000 nodes on one screen. It's just a limitation of JavaScript, it just doesn't work. But important to understand that graph databases are not only those visual links, it's also a data set. You can represent data as columns. And that's what you have to when you think about graph databases, it's not only graphs, it's regular tables too. So how do you gather data? So that I took from someone, copied, all right. So friends don't let friends dig through data. So my nights I spent creating something called Network Discovery and Management Toolkit. It's something that, coupled with Ansible, can provide you a data discovery in a smart way. So ordinarily, we were collecting data using Rancid, where we were prescribing, let's say, show IP route, and we'll collect show IP route and then we'll store it. The problem is that if I try to do show IP BGP table and I try to discover all my neighbors, and then I want to collect routes that I received from neighbors, I cannot do that with Rancid because Rancid doesn't know the IP addresses of the neighbors. And if you have enough neighbors, you cannot type them manually. So that's how I thought about creating this toolkit, because I thought, like, let me do something that would accomplish what I need. Basically, what I want is a lot of data, all the time, continuously, and predictably. So here's how we do that. Ansible, that's a sign there, a sign. There is a plugin. It's a Python file that basically acts as a bridge between Ansible and expect. And then expect script interacts with individual devices. Not only it can interact with devices, it can interact with anything. And that's what we'll go into through the next slide. It is all about eyes, not APIs. It's all about interfaces. There is nothing that makes me more happier than me being able to access a database via Unix domain socket without a password. And when I dump that data, it really feels really good. All right. So when you think about interfaces, that's what you have to think about. So there's web browser impersonation. Someone who doesn't provide API. Okay, let's try to figure out how the web interface works, and maybe I will be able to subscribe to some feed that they publish out there to get that data. There is message bus subscription. So for example, you see it unprivileged account, you see it on the system, and you figure out for yourself, okay, how do I get the data from the system? So there is, in operating system, there are message buses. So theoretically, you can hook, if you have privileges, and because our systems are mismanaged in a lot of cases, you can hook yourself up to a bus and listen to the messages that get exchanged. Same about operation systems and application hooks. So what is expect? It's an interactive program. If someone heard about TCL, it's that. So years ago, it allowed us to basically wrap around some kind of executable and being able to send a command, wait for certain output that we can predict, and send another command as a follow-up. So what's an interactive program? SSH, Telnet, curl, wget, minicom. So it's like if I want to use this to access a console port, let's say I have physical connectivity to a terminal server and I want to configure a device that doesn't have IP, anything configured with it, I still can connect to a terminal port and now interact with the terminal port via some kind of serial connection. Right, so we are, all right. So the system is built in the following way. So inventory is like a regular Ansible inventory. Think about orchestration tool and inventory. Playbooks. This is what you need to do with the data. It basically tells like instructions like what do I want to get. Credentials vault. If you store, anytime you use management system, like orchestration system, and you put your credentials in plain text, you basically don't care about security. So Ansible has this thing about Ansible Vault, and it allows you to basically encrypt your data, encrypt your passwords. The thing is, it doesn't have a good credential system, so I developed my own. It's basically, it's in the code. You can go in, and it's called callback plugin. So whenever Ansible starts and executes the task, there is a hook there that you can attach to, and you can read through some external data, let's say like that file, and you will be able to get credentials to access devices. So in theory, you can have your credentials that match regex expressions for all sorts of devices. And they can have priorities, and you can read about that. So in the interest of time, I will just continue. Data collection is very simple. You say, this is data collection against a firewall. You say, I collect all relevant output. I output that to a path. I don't want to check SSH keys. And if there is an error, I want to continue, because you want to fail. Data analysis functions. So data analysis functions are based on the following. There is a bunch of YAML files in that repo that provide the basis for the algorithm to discover new commands to run on a device. So a basic premise, you run show running config or show version. It gives you an information there. Let's say router BGP. You know that as a follow-up command, you want to run show IP BGP summary. And then after that, after you run summary, you want to run commands against neighbors. And that's what I call derivative commands. Factors. So in Puppet, there is a thing called factor, where you run a command against it, like before you run any job on Puppet, you discover facts about it. So I created a similar thing that would match a regular expression, and it will either add facts or have existing facts there, right? So in here, it's OS vendor, that's Cisco, OS name, OS class. Later on, you can match against those facts in the patterns. So sometimes you need to set a prompt, because expect works with prompts. It needs to know prompts. So you would set prompts. You would set an exit sequence. So for example, if I'm against a Linux box, what I want to do is I want to clean up my history. I don't want to people know what commands I run. Especially, I will do with output filters. So you would want to, sometimes you collect the data and you know there are passwords there. So you will basically put a filter replace saying, oh, this is like username. If you see a line of username, remove the line with zero output, and that would, you will avoid unnecessary data exposure. So reference tags and data logic, the way it works is, the concept, you have some tag that says to you that that's a configuration. And then once you had that tag, you can correlate later on in a game. You say, if I have tag binaries, so for example, I run a command to find all the things, all the binaries in my path. I can later on say in the rule that I want to run OVS VCTL, basically Open vSwitch commands, to get the overlay information. It will only run if the binary output had something to do with Open vSwitch. Error handling. I want to fail, so I describe what is the output that commands would fail. So in this case, if I see a warning, that's a failure. Exceptions, some commands, you would see that inherently, you would see the failure. One of those is showTech. showTech is a collection on Cisco devices, is a collection of a lot of commands, and some of them would fail. So here's an algorithm. You take configuration, you take basic sets of command line sets, and then you create a lot of derivatives, and you go and you dig deeper. There is basically all the operating systems that have commands there, so you can check it out yourself. And here's an example about show IP BGP route. There are derivatives there. Important things like once you match a pattern, there is a certain derivative pattern that goes with it. In the interest of time, I will just skip to graphs. So how do you store data? When you output, when you produce reports, it produces reports. You have to provide metadata. Metadata later on can be captured by AI system, and you will be able to get metadata in JSON and YAML, and later on you would correlate. That data is important because it provides description for what you captured. Git commits, branches. So do that. Anytime you produce the data, make sure you integrate yourself with Elasticsearch. push the data through API. JUnit files, generation of JUnit files. So here's how you do the graphs. So there is an XML and there is RDF. RDF is a format of triples, so there is node-node connection. Here is the interface. Here's a router interface, let's say a property and some value that was associated with it. So the connection there it could be a property, the middle ground there, like configured MTU, 9000. So it could be either a property of an interface or it can be a relationship to a property. Here is how you can see that in a different representation. And those different data can be also correlated in triples. Ontologies. So this is someone created an ontology and published that on the web, enterprise grade. I advise you to look into that. And here is Sparkle inserts. That's how you get data in the graph database. You create a resource entry. It's like a URL. So instead of ID, it's a URL. So you have to create those URLs, and then you create the properties. So this one, you created a dot. This one, before that, we created a device. Here, we created an interface. Here's how we connected the two dots. We took a resource identifier from one node and the other, and we connected it by a relationship. So my time is over. I beg you, please take this presentation and look it over. If you have any questions, please reach out to me. Thank you.
Okay, thank you very much, Paul. And Paul's also a licensed attorney and does some pro bono work. So if you have legal advice you need, you may want to grab him for that too. Okay, next up is, and he's here to talk to us about interactive coding with big data analytics. And Sam has, he's just recently back from Albania, I understand, right?
Yes, that's right.
And so he is now a recognized expert in where to go to get peppers in yogurt in Albania. So, you can also stick around and ask him questions afterwards about that. No, I'm sure he'll share his knowledge.
And in all seriousness, Albania has a wonderful tech scene. Really, really cool. If anybody's curious about that, come find me afterwards and I'll talk to you about it. So I'm Sam. I work in Mozilla, as per the gracious introduction there. And I learned on the job how to work with terabyte scale distributed data. And my goal in this talk is to save you some of the hair-pulling, what the heck is going on learning on the job that I did. And in particular, I'm going to give you a clear mental model for what is different when you are working with clusters of computers and terabytes of data. And I'm going to offer up a core technique, which it seems to me deals with the specific problems that I've encountered in a few years of this and in consulting with a few dozen and training my colleagues as they come onto the task. Let me go back one quick. And this is, in case it isn't obvious, a talk for coders. So these gentlemen are two people to whom everyone in this room owes a great debt. They gave us Unix and C. And there they are developing these wonderful tools that we all rely on every day. And they also gave us printf. And the print there is not a metaphor. There's a big roll of paper there that if they want to inspect the state of a variable to figure out what's going on in their function that they didn't anticipate, well, they print it out on paper. And I would argue that what they're doing there, printing out things on paper to see what's up with their code, is the heart of the craft of coding, right? You take some working code, you make a little change, you run it, and if you're confused by what happened or an error, an exception's thrown, you either step through it in a debugger or you drop in a few print statements if you're old school like me, and you observe the program state so that you know what the problem is. This is super, super basic, but I want to be really clear about it because it is what goes away when you're dealing with distributed big data coding. So this is a Python prompt. This dates from about 1990, which is closer in time, let us note, to those two gentlemen than today. Yet we still work with it. It's tremendously productive. It looks like a bash shell, and here it is giving us some reasonable sized local state, in this case, the directory path that I'm working in. Here's a more modern interface. This one's about 10 years old. Have any of you used Jupyter Notebooks before? Yeah, a bunch of you. Cool. So this is a web page that is sending strings that I've typed in of Python through a WebSocket back to a Python interpreter on a Unix machine, and then returning the value of the expression after they've evaluated it. So this looks like this, except, it's black on white instead of white on black, and, I can use my mouse. Pretty cool. Well, this is also the interface that is used for a lot of distributed big data coding, and guess what? Things are a little different underneath the hood. So this is an amateurish diagram because I drew it. I drew it because I could not find a good professionally done diagram that I thought did justice to the architecture, and I would argue that this even itself is an oversimplification. So what we just looked at here, this screen that I'm typing into, is the little blue box at the bottom labeled My Web Browser. That is SSH tunneling into Amazon Web Services, which happens to be my cloud provider, connecting to a Jupyter process running on a cluster I've started up on the master node, which is connecting to IPython and evaluating that Python command I sent. Python, in turn, is a child of Spark, which is a distributed computing framework, which is very popular. The reason we're using Python is that data scientists know Python and not Scala in general, which is the native language of Spark. And so what happens when you distribute a command is it gets serialized and sent through the Spark chain out to distributed Python workers. And then, of course, all of this, the entire point of spinning up a compute cluster is that we have a lot of data, right? And in our case, it's on S3. And that line cutting across the corner there is my attempt to draw a curve with a really big diameter. And the thing here is that scale is hard for our little human brains to reason about, right? How many people have seen this image before? It's awesome. Look it up on Wikipedia. So it starts off, the first two are planets in our solar system, and the biggest object in one thing is the smallest object in the next, right? And what you see if you look, particularly at numbers 4 and 5, is that the tiny little dot in number 4 is actually much bigger than our sun, and the tiny little dot in number 5 is much, much bigger than this thing that's much, much bigger. So this is orders of magnitude. And we can't really represent them with one image. It's too hard. And that's the challenge I face when I was drawing this. And it's a challenge you face in your head when you're trying to cope with this stuff. You're not going to directly observe program state if you've got billions of rows. If you step through it, you will die of old age before you finish. So what does this mean in practice? Here is a traceback that happened, true story. I had some ETL code. It was working great. I'd moved on. One day, I get an alert, there's a problem, and I start to read this traceback. Okay, that doesn't tell me anything. Let's scroll down and see what's really going on. Well, 30 more screens of nonsense, and I get to this. Everybody figured it out right now? You see the root cause? No, I don't see the root cause. This traceback is not very helpful. I need a technique that is equivalent in power to the one that we've been relying on for 40 years. But I can't use that same technique. I need a new one. So the good news is that as you stumble through these problems, you'll realize that there are 3 kinds of problems you're going to encounter. Crashes in 2 flavors, slowness, and then one that is arguably unique to distributed big data programming, which is that everything seems to work great, but you don't believe the results. And how can you double check them if the results are generated from billions of rows? I'm also going to argue that there are only a few underlying causes, and I'm going to go over these in detail, so I'm not going to read this slide to you. But great, Sam, thanks for the taxonomy. You haven't actually told me how I can solve this. I need to map from what I'm experiencing to what Sam up here is asserting are the underlying causes. And the rest of this talk is about how you do that. So recall that when you drop a printf into a little local function with human scale values, that you're making the program state observable. And that tells you what the problem is. Well, when the program state is the size of some giant star, you can't do that. But what you can do is make the problem state observable. And to make it observable, you've got to make it local. If it's still out there in the cloud, you can't see it. And then the second part, is that when you scale out and up, you need to do so in discrete stages so that you can triangulate better on the problem. So here is something you might see. You might see a traceback. Previously, we had a traceback that ended with an error occurred, which made me want to throw my computer. This one ends with a type error. Is anybody intimidated by type errors? Have any of you ever had a type conflict in your code? I would guess that every single one of us does on something like a daily or weekly basis. Type errors are the bread and butter of debugging code. We all know how to fix them. And what had happened in this case was that there was a none that had crept in where I expected there to be a string that looked like a floating point number. That's no big deal. What I want you to notice about here is that if I get a type error in the traceback down here in this box in the bottom, that type error originated out in one of those yellow Python worker boxes out in the node. So the key, this core technique is being applied by the framework. The framework is taking the problem state, which happened way out there in the cloud somewhere, and it's bringing it down and putting it in front of me. It's making the problem state locally observable to me. Now this, you might argue, is not very interesting, except I want to show that the two techniques, the Ritchie and Thompson technique and this technique I'm arguing, in this case are the same. Now let's look at a slightly more interesting case. So this is something I did one morning when I hadn't had enough coffee. I wanted to grab the week's worth of data, so I dropped an ISO formatted date string into a where clause to filter down 10 to the 10th rows into roughly 10 to the 9th. And there were no rows in line 2, right? I should have billions of rows and I've got none of them. What the heck? That's impossible, right? I don't expect this. Well, it turned out I was lucky. I had made such a bad mistake that it applied to every single row in the entire data. Can everybody see what the problem is? The date was formatted differently and I was doing a string comparison, right? So that meant that the bounds were, lexicographically, the bounds of my where clause were totally outside the way the dates were written there, and so no rows were matching the clause. All I needed to do was take the hyphens out of my where clause, and it would have gotten the dates correctly, right? So in this case, I made the problem state locally observable by grabbing an arbitrary number of rows. And in case it isn't clear, that .take function is saying, go out to the cluster and just give me 40 rows. I don't know which ones they're going to be, but just give me 40 so I can start to play around. So the key technique of making the problem state locally observable in this case was easy because the problem state was in every row, right? So at this point you're thinking, great, Sam, this is not rocket science. I probably could have figured this out by myself. And indeed, pretty much everybody does who's doing this coding. But there are trickier problems. So let's say you've tried these two things. You've read the traceback. You've looked at a few rows. There's no clue. What do? You go on to the second point. You start scaling up and out, but you do so in steps. The first thing you want to do is you want to scale out without scaling up. So you had a traceback, you had some crazy problem you don't understand, you bring in a little data, you run it locally just the way Ritchie and Thompson would have. Everything's great, there's no problem here, but you know there's a problem out there. How do you get from here to there? The first thing you do is you take the code and data that worked perfectly locally, and you distribute that code and that data and run it again. There is a chance that just the act of distribution will reveal it. And on the screen is an example of how it can happen in Python. If you are relying locally on some code that you haven't installed on all the different Python workers out in your box, you'll get a problem. Let's say you get past that one. Now we're getting into more interesting problems. So now you want to start scaling out, taking more and more data, and do so in chunks. Probably don't go to 100% because nothing's going to change, right? At this point, you can expect one of three things to happen. Either you're going to get another what I'm calling code data problem, like that type error that we've seen before, or you're going to get a problem that looks more like the one where there were 30 screens and it ended with an error occur, and I'm calling those toolchain panics, and I'd actually be curious to know if anybody knows of a better term of art for that. An exception or an error which is in the stuff you're relying on and not in your code. And then finally, you might see that runtime is increasing exponentially, which means you're headed for a toolchain panic. So toolchain panics are pretty straightforward, easy to recognize. It's not in your code, and it's in some namespace of something that looks like the framework you're using, right? Pretty straightforward. So let's say you have a code data problem. You've got this type error when you're calling float, but it's somewhere out there. It's not in your sample data. What do? Well, you change your function that is going out and touching every node in the cloud, and instead of calling float and blowing up, you tell it, call float. If you don't blow up, don't do anything. Return nothing. If you do blow up, catch the blow up and return that row. And then you'll have a data set which consists exclusively of the rows that your code can't handle. And then you can bring them back locally, look at them, and see, oh, there's a none there, because 1 out of every billion times, the thing that generates this floating point number is not correctly initialized, but it happens so infrequently that I never saw it in testing. By the way, this is the root cause variance. So is everybody familiar with the idea of variance? So the idea is, I think I'm going to get a string that is non-empty, that has numerals and exactly 1 decimal point in it. And that's the domain in which I expect the data to come. And actually, there's some other thing out here, in this case, none or null, whatever you want to call it. How many people know what cyclomatic complexity is? See one hand. So the basic idea is every time you see an indentation in that enormous block of code that you can't read, don't try, it's too small, unless your eyes are way better than mine, you add 1. And this is all one function, and yeah, it's my fault. It's way too big. And in software engineering, when you're trying to measure code quality, one heuristic people will use will say, let's take the cyclomatic complexity of your functions. And there's a rule of thumb that if your cyclomatic complexity is much above 10, that indicates that your code is a complex state machine and there's probably bugs hiding in there. So I wrote this, and you know what? There were no bugs hiding in it. Yeah, it was long, but it worked great. Only thing is, when I ran it, the results it returned, it didn't crash, but the results it returned made no sense to me. So looking at this, when I wrote this, I had an idea of what it was going to do. And in some of those if clauses there, some of them are like, yeah, once in a great while this might happen, but probably not. So you know what? If it does happen, just throw away the data, because it's only 1 out of every billion rows. Oh, by the way, don't do that. But it turns out, actually, that worked for a while, but then somebody changed something upstream for me, and that thing I thought happened only 1 in a billion times happened 2 out of every 3 times. And suddenly, my mental image of the state machine that was being executed when my code was running was way off. Now, I can't go out and read all billions of executions. But what I can do is I can ask the framework to count them for me, and in particular to count the edges, count at a branch, count at a loop, and go through and say, okay, here's the hotspot in my code. Here's what's really dominating the processing effect. Does that make sense? This is the one I struggle the most to explain. So the next thing that's going to happen is runtime's going to increase. And those of us who got computer science degrees, somewhat belatedly in my case, know about exponential algorithms. And that means you either are going to hit a toolchain panic, or you're on your way, or else things are just taking long and you're wasting a lot of computing power. A toolchain panic, I showed you the text earlier. What it basically means is one of these edges breaks. Sometimes it's one of the green boxes, but usually it's one of the edges between one of the green boxes. And as I said, this is oversimplified. There are way more edges. To lighten the load and prevent your exponential algorithm from taking out your cluster, I suggest 4 approaches. The first is, if you're doing a many-to-many comparison, before you begin, localize the data. So if you tell the cluster, I'm going to group by user ID so I can count how many unique users we are, tell the cluster before you do that counting, partition the data on the clusters by user ID. And when you do that, not only will it mean that all of the user IDs, they're going to be counted multiple times or on one node, it'll also mean that the framework knows that, and it won't try and go out across the network to fetch other data. And you'll get an enormous speed up. The other thing that can happen, which I'm not going to discuss real quick, is that you might just have really skewed data, and the arbitrary allocation that the cluster does may end up all on one node. So let's say that you're using your exponential algorithm. Exponential algorithms look awful on the way up, but the secret is that if you turn around and look at them the opposite way, suddenly they look pretty good. If doubling the data size means that it runs 4 times slowly, well then cutting the data size in half means that it runs 4 times as fast. And so if your function is associative, let's say you're processing a month of data day by day, if you chop it down into 2 weeks, you're going to get a 4 times speed up. I have run over time. I'm not going to discuss sampling. How many of you have done work in statistics? How many of you think I can give you a degree in statistics in 1 slide? Yeah, me neither. Oh, you do? Oh, thank you, sir. You're very gracious. Statistics is powerful, but you have to know how to do it. And then finally, I want to highlight point number 2 here, which is let's say that you've run an analytic function and you're really surprised by the results, and you've double-checked anything and you can't find any mistakes. Consider the possibility that you did a great job and you learned something about your data. Thank you.
Okay, so we do have a little bit of extra time just because of all the speakers were so good about keeping to their 20 minutes. So are there any questions for Sam? Yeah.
So I work a lot more often in this sort of paradigm you're talking about, but I'm also trying to pretend that I'm a good software engineer and do some good unit testing. What I find impossible is trying to large data sets, unit tests, trying to find those strange cases in any way that doesn't take 16 hours or whatever.
Listen to this guy's sharp. So in an earlier slide, I had that line about you can't read 17 million values, and then below it there was a block that said you're not going to write 17 million unit tests either, right? So pre and post conditions and Bertrand Meyer style contract by programming aren't going to work. So what do you do? The short answer is I don't know. But my favorite thing to do is to combine acceptance testing and monitoring. So acceptance testing is, I've written this analytic function or this ETL function, and I'm pretty happy with it. And it says that we have 87,314,22 searches in Germany in this month, right? And then I just use that as my acceptance test as I keep going. More interesting to me, it seems to me, fundamentally, is integrating monitoring. So stop thinking of yourself as producing source code and think of yourself as your distributed system is this organism that's out there on the network doing stuff and producing outputs. And what you want is a zookeeper who's going to go along and look at it and say, do you look healthy? So this is not sysadmin style monitoring. This is actually end user or client monitoring saying, the line of users in Germany in the month of March just tripled. Did we actually get 3 times as many users in Germany? So have human beings look at graphs and reports which summarize the whole state of the computation chain. And ideally, most of your code is generating things that people really care about, right? So most of your work is meant to give numbers to people who can make important business decisions. So if they're looking at those decisions, that's a great QA. Now the downside is that some super important person is catching your bugs, so. Yeah. But great question.
Other questions? No? Anyone? Going once? Going twice? Okay. Well, thank you very much, Sam.
Thank you.
So, and thanks to all of you, and thanks to all the speakers for your not only giving us great talks, but keeping to your time. And thanks to that, there's a break next, and so I invite all of you to go and enjoy that. And thanks for showing up for our block of sessions.